Good evening, good afternoon, good morning, and welcome to the Trillium Flow Technologies webinar on low-flow, high-head pumping applications. I'm Steve Osborne, and I have been with Trillium Flow Technologies for over 40 years, and I help to serve with multiple product lines of our specialty pumps in Trillium Pumps USA. I will be joined today by Sam Eccles. Sam is the product director for Trillium Flow Technologies, and he has over 16 years of experience in the industry in a wide variety of different areas, including both quality and product roles. He holds an engineering degree as well as a MBA.
Perfect. Thank you very much for the introduction, Steve, and thank you everyone for joining us and giving up your time. So just a very quick recap before we enter the webinar. We just want to give a bit of background about Trillium. We recognize we're recently new name, so we want to make sure that everyone's aware of who we are, how we're made up, and the brands that fall within the Trillium portfolio. So as you may imagine from the start of our name, we are made up of three core elements. They are pumps, valves, and service. We do also have a turbine brand within our portfolio, as you can see. But the main focus of what we do is around pumps, valves, and the service element. The service piece does cut across all rotating equipment and is not just limited to supporting the brands you see on screen. One of the things that we do want to stress and make people aware of is these brands have been chosen to come together. They are not just brands that have fallen together over time, as with many legacy companies in existence. These are very complementary pieces. So if we take the pump portfolio, just as one example, you have the Begerman and Gabionetta pumps that really lead our API portfolio, typically known as process pump manufacturers within API, but actually the more you dig into the install base, Gabionetta has pumps that are almost up to 10 megawatt. So these are really huge pieces of equipment within the rotating equipment field, and are not just at the smaller size that they're more well known for. You've got Flowway that really are the leading brand for VTPs for the North American market. Again, very strong brand recognition, very well known, and a brand that's been established, as you'll see on the next slide, for almost coming up for a century. And again, we're going to talk a lot more about the WSP and Roto-Jet brands that are on there, so we'll just focus very briefly on the Thermomechanical Pompe brand. This is the most recent acquisition from a pump portfolio point of view, joining in April 2022 within the Trillium Group. And that really expands our service portfolio, not just in terms of footprint around the world, but really in terms of competence and in terms of giving us something that none of the other brands can replicate, and allows us to become a really leading service provider across all types of rotating equipment. So again, just to make sure that you're aware, we're not going to go through every brand on here in the interest of time, but if I can just pick out some of the key highlights, these three here all make up our pump portfolio. And you can see this is when we start to talk about 3 centuries of experience. You can see where we get that from, with the Gabionetta brand in 1897, TMP that were formed in 1912, and Flowway in 1934. And really mine and Steve's role within the organization is to make sure that we leverage all that IP, technology, and expertise within those brands, and look at how we bring those together to make them stronger as one business and more than just the sum of their parts individually. Okay, so for those of you who may not be too familiar with centrifugal pumps, we just want to make sure that we don't get lost in the terminology at the start. So this is just a very high level overview, and it's the API standard designations. And just to give general terms for some of the pumps we'll discuss as we go through the webinar today. We recognize that we're not necessarily just talking about the API industry, but these terms are generally used even to describe other types of pumps in terms of construction. So just as a very quick overview, you have OH, which stands for overhung. You see 1 and 2 are horizontal, and the rest are all in the vertical orientation. BB stands for between bearing, so you have a bearing either side of the pump's impeller. All of those are in the horizontal configuration, and then VS as vertically suspended, as you can see there. Okay, so with that introduction, what we really want to talk to today is the challenges with low flow, high head applications. So we really want to talk about why these are viewed as problem applications, what some of the solutions are, and really why they're so misunderstood as a general area of the market. So there's a variety of reasons for this. One of the first things we want to do is define what we mean by low flow. And typically we'll talk about anything that's below 100 meters cubed an hour, 440 US GPM. and above 150 meters, or 330 feet. The reason that these become so problematic is you can see from the chart on the right, for any given centrifugal pump, this is a typical head flow curve in blue and an efficiency curve that you can see in gray. At any given point, it's going to have a best efficiency point. This is where the pump is designed to operate. This is where vibration is at its lowest and the pump is providing its optimal efficiency. As soon as you move away from that, efficiency tails off, vibration increases, and ultimately you get outside the preferred zone, into the allowable, and ultimately back to the limit that will be defined by the pump manufacturer. But as a general rule of thumb, the further away you move from the preferred operating range, the less mean time between failure you're going to have, the more maintenance you're going to need. Two things that bring down centrifugal pumps are bearing failure, seal failure. Number one cause of those from a mechanical point of view, not a process point of view, is vibration. So anything we can do to keep the pump operating here is going to improve uptime and reduce the number of problems end users have to deal with. So one of the reasons why these low flow, high head applications are so challenging is inherently, as you can see from the HQ curve here, the further back you go, so the lower your flow is, the higher your head. And it's very common to get these low flow pumps operating in this region. And this is when you have a lot of recirculation within the pump, a lot of increased vibration, and ultimately you run into failures at site. In addition to that, there is a huge amount of choice at this area of the market. And one of the things that we hope we get across in this presentation is there is not one right answer. And anyone that tries to say that this is a one-stop shop solution for everyone's fears is oversimplifying. We're going to talk about solutions that Trillium don't offer. We're going to explain when they have their place in the market. We're also going to talk about some of the options that really only we offer and when they have a place in the market and when they have their limitations. We want to make it very clear there is no one solution that is best all the time. And it's a very, very complex solution, really, to evaluate which of these technologies is the best fit for a given application. Also, the technologies are very, very different, as hopefully we'll show you in the next few graphics. There are some that are conventional centrifugal pumps that are very familiar. There are some reciprocating positive displacement. There are some high-speed geared applications, and there are some pitot tube designs. Now, which one of those feels normal and which feels strange will very much depend on an end user's experience. But we're just trying to highlight there is so much choice, so much flexibility within this operating zone. And this is an operating region where you can cause a lot of the problems on site because it's very easy to make the wrong choice. Other reason, in terms of value, these are relatively low cost pumps that we're talking about because they are relatively low power. And with that, your motor's not very expensive, your base plate's not very large, your packaging options are not very expensive. There's typically not that much NDT on these packages compared to some of the higher energy machines. And as a result, they get a lot less scrutiny. So you combine a huge amount of choice with a low value package that doesn't get scrutinized as much at the EPC or the engineering assessment phase of the project. And often you can end on the wrong technology being chosen. Combining that, you can end up in a position where, for a variety of reasons, you may select a pump that is operating exactly at the design point, but when it's fitted at site, in reality, it's operating way back here on the curve. So you get in a pump that, yes, on paper looked a perfectly good fit, but by the time margins of error have been built in, or maybe the process conditions have changed on site, you're then starting to operate a pump in a zone it was never designed to run. And that's one of the other problems. And in general, if you were to talk with any end user, most of their problem applications will be pumps operating within this low flow, high head range. So that's the problem we're trying to solve. Over the next 5 minutes or so, we'll just run through what some of the standard solutions are. And then Steve's going to take you through our pitot tube range and explain where that has its place in solving some of the problems in this market. So the number one, the most common pump in the industry, almost any industry, is this end suction, top discharge, very standard centrifugal, single stage, overhung pump. And it's an OH2 per the designations we talked about earlier. The advantages to this, they are very low cost. They are very well known. Probably 3/4 of the pumps on a refinery will be this kind. If you're in a chemical plant, water treatment plant, most of the centrifugal pumps will look like this. Relatively low head. So in terms of some of the challenges, as we need these ultra high pressures, these pumps become unsuitable. And equally, as we go to very low flow. So if we talk about getting down to below 20 meters cubed an hour, 90 US GPM, these pumps will start to struggle, just because to get these passageways cast becomes very challenging. So there's a finite size that you can go down to, and then per the chart we showed previously, you end up operating at a much lower flow than the pump's designed for. The pump will vibrate more, you will run into more problems. In terms of the head limitation, you're really limited by how large you can make this impeller. You know, we are governed by API deflection limits at the seal face here. So this is an overhung shaft and an overhung bearing, and we can only run these impellers to a certain size before we just get unacceptable deflection levels, which would ultimately cause in-seal failure, both through vibration and through shaft deflection. So that means that for the very highest head areas that we want to get to, these pumps do run into limits. But in terms of the vast majority of the market, this is the go-to solution. So if we then look for something that's slightly higher head than a conventional OH2 and something that can operate below that 20 meters cubed, 90 US GPM mark, you would typically go to what's classed as a low flow OH2, or often referred to as a Barsky OH2, just because of the change in impeller. So this runs a Barsky impeller within a diffuser that you can see in green here. And this really just allows us to get to much, much lower flows in a reliable manner. And again, the advantages here, very low cost, significantly higher head than a conventional OH2, and the ability to go way, way back in terms of flow rates compared to what you would have seen on the previous pump. Now, as with anything in engineering, you don't get anything for nothing, and the price you pay is these are very low efficiency. So typically these units, it's not uncommon to be below 10%, and that's 10% at its optimal operating point. So you start to operate away from that optimal point, you can be 5, 6, 7, very commonly on this type of pump. Now it will operate reliably there, but it's not efficient. And again, if you have one of these pumps, that's not a problem. If you have 100 of these pumps, that starts to become very significant. And that's where it's very important for these low flow solutions to look at them as a holistic proposal and not always just in isolation. Because in isolation, it will often make sense to go down this route. If you have more than a handful of applications, it may not. You know, it's important to note, energy cost is by far and away the largest cost that's associated with installing any piece of rotating equipment, especially pumps. So if we then get onto units that are for significantly higher heads, so these will go well in excess of 1,000 meters, you know, over 3,300 feet. These are really a huge order of magnitude more expensive than the previous pumps we've shown, as you can tell just looking at the construction. And these typically can be 5, 6, 7, 8, 10 times more in terms of cost, but they will achieve duties that the others simply can't. And when these are operating at BEP, they are much higher, they are much more efficient. Typically, you'd be looking at 60, 70% efficiency at around the 100 meters cubed mark for this type of pump. And really, they are often the only option for some ultra high head applications. However, the challenges that they come with, very expensive as we've touched on. And really, if you start to get below 60 meters cubed an hour, you're really going to start to struggle with these. And at that point, you have two options. You can either recirculate some of the flow, and then what happens is the pump is going to look like it's very efficient, but when you look at it as a system and you factor in that recirculation, it will become very apparent it's not an efficient solution. Or there are some Barsky type multi-stage pumps that you can go to within the industry, but they are not a common solution and they are not widely accepted within specifications at present, although that may change going forward. And then if we look at option 4, this is probably what most people think of in terms of when they think of a low flow high head pump. It's a OH6 construction, as you can see by this graphic. This is really quite different to the other options that we've talked about. So this really has the conventional motor in a vertical orientation with a gearbox, and then typically an impeller running 20,000 RPM, when everything else that we've talked up to this point really would be capped at 60 hertz two pole, around 3,600. And typically, because of the speeds that they're running with this impeller, they need to then run an inducer to make sure there's enough suction pressure within the pump. Advantages these give you is they are a very small footprint. Particularly with being vertical, they take up very little space. They are very cost effective at the point of purchase. So the upfront CapEx cost is very low and they are very favorable in terms of those assessments. But as we've mentioned before, and as we're trying to say all the way through, there is no one size fits all, and these do come with some limitations. So the operating window is small on these pumps compared to all the other units we've looked at, and that is largely due to the inducer. Steve's got a slide that he'll talk to you later explaining that in more depth, but really for the purpose of this overview, all you need to be aware of, there is a much less flexibility. So if you are certain where you're going to operate, these are a very good solution. If the process is going to be consistently turned on and left running, very good solution. If you're going to have upset conditions or you need to achieve a wide range of duty points, these can be very problematic. And often as well, it's not just about, are you going to achieve a wide range of duty points? It's how accurately are you able to predict where you need to run? Because it's very common in the field for these bad actors that people have to find that the equipment that was ordered is perfectly in line with what was requested, but the unit was never going to operate at the required duty. And that's a common source of issues that we see across the pumping industry, because it's hard to predict accurately where these process conditions are going to sit. Other challenges, complexity to overhaul. As you can see, the sheer number of components here, you are dealing with a gearbox, changing out the impellers not as easy, getting to the mechanical seals not as straightforward as some of the other designs that we've looked at. And because of the tip speed the impeller's running at, you do run increased wear rates, so you do get through more spare parts compared to some of the other solutions. The trade-off, these can hit head limits that you would only hit otherwise with the multi-stage BB3 and 5 that we showed earlier. Okay, and then the last of what we're calling the standard solutions is positive displacement. So there are many, many types of positive displacement pump. We are just showing one of them in the reciprocating pump. You can think of this very much like a car engine. It's got the same valve gear up ahead and a series of plungers, you know, instead of the pistons you would have in your car engine. But in terms of principle, it's largely the same. These are very high efficiency, very compact. You know, you have the ability to put the drivers directly above the pump with belt-driven options. These can be made and fit into a very, very small space, reasonably cost-effective as well, obviously depending on horsepowers and flows. Challenges that come with these, you have a lot of pulsations downstream of the pump to manage. These can be alleviated with pulsation dampeners, but you then take away some of the advantages because the skid becomes less compact and it becomes more expensive. Also, lack of familiarity, particularly outside of North America, I would say. Most people just won't consider these. It's not even open to be debated. And really the other, and probably the main challenge here, is they do use a lot of spare parts. So the mean time between failure and overhaul isn't great, which means if you need something that's up 100% of the time, you're going to have a spare on standby that's also piped in. So then if we try and talk about another option, that's something that Trillium is relatively unique in offering, it's our pitot tube pump range. So we refer to this as the Roto-Jet series, and these are pumps that can be provided in a variety of configurations. So we're showing it here in a between bearing configuration, but we'll show you later on it can be done in a very similar way to the overhung pumps that we've shown earlier. Advantages here that this operates is it gives very, very reliable low flow, high head operation. Much more so than the other designs we've touched at, it allows versatility. So where you want to operate on the performance curve does not impact mean time between failure. And Steve's going to talk in detail about why that is, but that's the main advantage these units have. No pulsations, so we don't have the challenge that we talked about with the recip on the previous slide. And if you were to do a like for like for a same speed, OH6, these will operate at a higher pressure and deliver more flow. They're also very efficient within a certain operating window. If you are below, you know, in the studies that we've done, if you're below 100 meters cubed an hour, 440 US GPM, broadly, these will be more efficient. If you're at very low flows, so sub 20 meters cubed, 90 US GPM, there'll be a huge efficiency advantage for these. These can be 4 or 5 times more efficient than a Barsky OH2 design, for example. So again, a lot of advantages to these, but equally we want to be very transparent. There are some challenges. So these are less well known, which is one of the reasons me and Steve are talking to you now. There is less market awareness, and as a result, there's less acceptance within the industry. While these are not API recognized, they're listed in HI standards. They are accepted and specified by Aramco, so some of the most demanding customers in the industry. And finally, as Steve will explain with the video we have later, the pitot tube, which is the part that does all the work in this machine, unlike, think of it almost as the impeller as in a normal pump, is very sensitive to erosion. So if you have a process that doesn't have any particulates or contamination, that's not an issue. But anything that has any contaminants in, that is something that does need to be taken into account. Okay, so just one very quick overview then, just to show you. This is what we're classing as a low flow, high head range in general for the industry. And then we're just showing the Roto-Jet Tombstone in blue over that. So we do go out to higher flows, but where the Roto-Jet really excels is within this red envelope, because this is where you also can operate at an efficiency advantage. Now, there are reasons where you might want to operate outside of that, and efficiency is not your main driver. But the efficiency advantage really kicks in within that red envelope, as we've discussed. The key point we want to make here is these are not new pumps that we're showing. This is something that we've been manufacturing since the 70s. And, we have thousands of units installed in the field. Again, it's just about us trying to raise awareness. And as you can see from the two images there, we have the between bearing and the overhung arrangement. And with that, I'll hand over to Steve, who's going to take you through a bit more on the history and the technical benefits of the pitot.
Thank you, Sam. Just very quickly, we'll take a look at the history of the Roto-Jet pump. And as we first introduced and developed the pitot tube pump technology in the early 1970s, over 5 decades ago. Throughout the 1970s, we were quite active in development and R&D work, and were awarded over 40 patents on pitot tube pumps. In 1979, we introduced our first oil lubricated pump for the refining and petrochemical industries. And the following year, in 1980, we received the Chemical Processing Valor Award for a major contribution towards efficient plant operation. In 2004, the Roto-Jet pump was named the Technical Innovation of the Year by the British Pump Manufacturers Association. This was for our variable speed Roto-Jet technology using a switch reluctance drive motor. And then in 2016, we introduced our between bearing design with our patented flow-through technology that allows us to have a very reliable design of a pitot tube pump for refinery service. There are over 20,000 installations of Roto-Jet pumps around the world, and we have quite a history of working with a variety of applications in a wide variety of industries. We're going to go through a video here. It'll just take a couple of minutes, and I would like to kind of walk you through it. That we see the rotating element of a pitot tube type pump. The key working element of any pitot tube pump is going to be the pitot tube itself, which is always stationary. You can see on this design that the liquid flows through into a rotor cover, into the rotating assembly, where we have vanes that are cast in the assembly that will increase the velocity of the liquid. And the high velocity liquid will discharge into the rotating case, where the centrifugal forces will cause the high velocity liquid to turn at the same speed at the rotating assembly. It will then impact the stationary nozzle of the pitot tube, which will act as a very efficient diffuser to collect the liquid and discharge it out into the system. You can see through this design, it's actually quite simple. We have cartridge mechanical seals that are on each side of the rotating assembly. We have an integral gearbox that will increase the speed of the pump. There's no external lube. There's no wear rings required. And we're able to have a very robust, simple design that will get high heads at very low flows quite reliably. And of course, we have bearing lives that will exceed 25,000 hours here. And we'll just kind of quickly overview. You can see how the liquid enters in and then discharges out through the pitot tube. We can go up to, we'll go over the parameters, but up to 450 gallons per minute. So go up to some decent sized flows, and we can go up to 250 or much higher if we have a seal flush available. So we've got a very efficient design using the pitot tube pump technology, which is extremely versatile. And we'll have a couple of slides where we can go through and explain how we achieve that versatility and how we achieve the different performance requirements in pitot tube type pumps. So when we look at the Roto-Jet pump as an alternative to the OH6 technology, you can see the performance capabilities of the pump. As I mentioned, we can go out to 450 gallons per minute, or just over 100 cubic meters per hour, with heads that are up to 1,600 meters, or over 5,000 feet of head. The maximum suction pressure of 300 psi, or 21 bar, and without any flush at all, then the maximum temperature would be 250 degrees F, or 120 degrees C, but we can go significantly beyond that if we have seal flush available, and perhaps cooling water for the bearings if we get into the very highest temperatures. Our maximum speeds are going to be in the range of 6,500 RPM. Most of the applications that we're going to look at for pitot tube pump technology are going to be in the 4,000 RPM to 5,500 RPM. And the horsepower, the maximum power, is 400 horsepower or 300 kilowatts. There's quite a wide variety of different applications that you can find within the refinery services, as whether it's caustic processing and amine treating, as far as sour water, depropanizer, deethanizer applications, as well as injection services and transfer boiler feed reactor. We have pitot tube pump technology in refineries as well as on offshore platforms. So we'll take a look at kind of how the principles of the Roto-Jet pump and what some of those advantages are. One of the things is the pitot tube is always going to be stationary, and that stationary pitot tube is the heart of the pump. If we need to change the capacity of the pump, then we will just change the diameter of the opening of the pitot tube. So by changing out one component, we can go from a pump that is selected to operate at a very low flow rate to one that could go to our maximum flow rate by only changing out one simple part. The pitot tube is always going to have an opening at the 12 o'clock position that allows the pump to vent any gas that's inside. And then if the capacities increase, then we would add a second opening. So there would be an opening at 12 o'clock and at 6 o'clock. So there would be two openings on the pitot tube. It's always going to be stationary. There's never an occasion for the pitot tube pump to rotate at all. Our pumps are the ROFT design that we're looking at right now is fit with API 682 mechanical seals and a cartridge design. We also have gas seals that are available, and the seals are isolated from the bearings to prevent any contamination from seal leakage into the bearing housing. On our input shaft, we have Impro bearing isolator to keep the pump isolated from the outside. And we have discharge side, we have a 40-degree angular contact bearings, and on the suction side, we have a cylindrical roller bearing. And of course, the integral gear is cut to an AGM A12 standard, so it's a very reliable gearbox. We look at the gearbox case itself. It's a carbon steel sand casting, and it has a splash lubrication. You can see on the suction side of the pump, there's an oiler ring to provide the splash lubrication, and on the discharge side, we actually use the gears themselves to lubricate the pump. On the output of the rotating element, we have a 15-degree angular contact bearing, and our rotating element goes through a two-plane dynamic balance to ISO 1940 G1. The output shaft also has an Impro seal to isolate the bearings. As we've gone over the parameters, where the powers are up to 400 horsepower, 300 kilowatts, which is quite significant and will allow us to go through a wide range of applications. The bearing life is excess of the 25,000 hours. We can operate down to temperatures as low as minus 40, and we can go up as high as 250 degrees without any flush, and we can go considerably beyond that if we do have cooling water available. So the key advantages of this type of pump is, as been pointed out already, is the ability to operate across the entire performance curve, including back towards shutoff and beyond BEP. And we'll take just a look at why that is. And it's the pump is very easy to maintain with access to the mechanical seals. You don't have to remove any gearbox components, or you don't have to worry about making any difficult changes to replace a mechanical seal. You get a smooth, pulsation-free performance because it is a centrifugal design. It's very simple, only two basic working parts, and you have a lot of flexibility. By changing one part, you can adjust the capacity of the pump quite easily. The mechanical seals are only sealing against suction pressure. They're isolated from the bearings, and on our ROFT design, we take no exceptions to API 610. So when we look at the Roto-Jet pump as an alternative to the OH6, we'll start by taking a quick look at the NPSH required. You can see here on our diagram that there is a bowl-shaped curve that represents an NPSH requirement curve that is using an inducer. So the inducer is tuned to operate at a specific design point. And so that allows the pump to achieve a very low NPSH required at a given condition point. But as you can see from the curve, as you move away from that design point, then the NPSH required starts to increase quite rapidly. So if you have a condition where the pump is operating and has stable operation without any upset conditions, and is selected and is operated at the correct design point, then the NPSH is going to be adequate. If you move away from that in either direction, then you're going to start to see a significant increase in the NPSH requirements. When you look at the curve that is represented by the dotted line in our diagram, that's the NPSH required curve for the pitot tube pump technology in our ROFT design. And you can see it's a gentle sloping line that allows you to move along the performance curve without any drastic increases in the NPSH that's required to operate the pump. So therefore, you get a much wider operating window and more robust operation of the pump. And when pumps are designed, we'll take a look at what allows the pitot tube pump technology to operate at such a wide range of flow rates. But so when a normal centrifugal pump is designed, then the pump designer has a given operating condition of a flow to achieve and a head to achieve, and that becomes the best efficiency point. And so you select an impeller and design a volute to operate at that condition very efficiently. And so at the design point, or that becomes the best efficiency point of a centrifugal pump. And you can see at the best efficiency point, the pump actually has a very low radial load. So as long as you stay at the best efficiency point, then the pump is going to operate without any difficulties. As you start to move away from the best efficiency point on a normal centrifugal pump, you can see that the radial load that the bearings are going to see can increase dramatically. And so if we have oversized a pump, then we start to, or there's any upset condition and we move away from the best efficiency point and go back towards shutoff, you can see that the radial load is going to increase dramatically. And that radial load now causes an imbalance on the rotating element. And the imbalance on the rotating element turns to vibration and leads to shaft deflection, which is going to cause a shortened bearing life and a shortened mechanical seal life. And so that becomes the big issue when you move away from the best efficiency point. When you look at the green line that shows the radial load on a pitot tube type pump, you can see that the radial load that the pump is going to experience is constant regardless of the flow rate. And so that allows the pitot tube pump to operate at very low flow conditions, as all the way back to shutoff or beyond the best efficiency point, without seeing any increase in radial load. So you eliminate the shaft deflection you would see when you move away from the best efficiency point on a normal centrifugal design. So when we look at our ROFT design, you can see that we have an API 682 mechanical seal. It's the standard size 8. We fit the pump with both the John Crane and FlowServe seals. It can be fit with any API 682 size 8 design. We are familiar and use all API flush plans. We have the seal. Most importantly, though, the seal is only going to seal against suction pressure. We don't ever have to seal against the discharge pressure or try to balance out any pressures in the pump. And there's no shimming required in the cartridge design to when you replace the seal or assemble the pump. You just put in the cartridge and the pump is ready to go. So we'll look just briefly at some of the configurations that we have in pitot tube type pumps. Over the 5 decades, we've made a variety of pumps, and we still manufacture several technologies today. So we have also that are found in the API design and that are used in the petrochemical and refining industry is our model RO and ROH. It's an oil lubricated design, which has been around for a number of years and has quite a good reputation of operating reliably in refining and petrochemical services. It's an overhung design. It does have some limitations that we can't have quite as much range and capability as our ROFT design that we've been discussing. We have several designs that are used in industrial services, including our RG and 2100, which are both grease lubricated pumps, as well as the 2200 pump, which is an oil lubricated pitot tube pump design for the industrial services. We have our R11 design, which is a smaller version of the pitot tube pump, which allows us to operate at lower heads and still have a competitive offering there. And of course, as was mentioned, we have our variable speed design, our VSR, which has inherent variable speed without a variable frequency drive using our switch reluctance technology, which has become quite popular in certain industry segments. And so here you just see some examples. You can see on the right-hand side of your screen, you see our ROFT between bearing designs that we've been discussing. And on the left-hand side, you can see a representation of our overhung design. So now you only have a mechanical seal on the suction side of the pump, and you have the bearings or in the bearing pedestal, and you have an overhung load with a dynamically balanced rotating element.
Perfect. Thank you very much for that, Steve. So with that, we're just going to take you through a quick case study example that we have from, and this is something that wasn't produced by Trillium. This was actually produced by Aramco. This was something that we're happy to share the details of if it's of interest, and we can gladly circulate that. If you just reach out via the contact address at the webinar, we can send on the full paper. So something that was presented at the Middle East Turbo Machinery Symposium. And this was really quite a common story of where these Roto-Jet or pickup tube, pitot tube type pumps are best used and where they're most commonly retrofitted. So we mentioned before at the start of this, and it's something we want to continue to repeat the message on, there is no one size fits all. Any one of these technologies is not inherently better. It's just all about when each one has their place. And in this particular instance, it's about an OH6 installation, was fitted with an inducer. You can see that the units experience very high vibration, which ultimately, as we'll show you on the next screen, caused excessive volume and damage, resulting in many of these units being irreparable. And after several replacements of repeating the equipment, bringing it to as new condition, the failures reoccurring, ultimately deciding to switch these out with pitot tube type pumps. And we bring this up as an example because you can kind of see the values here. Catastrophic means run to fail. So you can see the numbers here. These are significantly more than the units would cost, whether they were an OH6 or whether they were a pitot tube type pump. So as we mentioned right at the start of this, because these are relatively low cost pumps, sometimes they're not getting the scrutiny. And that means they sometimes go into services that they're not well suited to. And you end up in a position where you've put the wrong technology in, and ultimately the technology is failing. It's not because the technology is bad, it's just because the design criteria didn't necessarily match the real world. And what was found here was once these were switched out with a pitot tube type pump, something that could operate away from design reliably for all the reasons Steve's touched on, these issues went away. There were no repeat problems. And again, it's not about saying there was a process problem, it's just understanding the right pump for that process. And again, it's not just the process at its design point, it's the process, how often does it start, stop, how often is there any variation, how often does something interfere that causes an upset condition. You only need the upset condition to occur once for one of these failures to occur. And you can see the values rack up very, very quickly. These values don't account for loss of production. These values don't account for man hours. These are just parts costs. And we just highlight this as one example that we have of many. So with that, we just want to give a very quick recap of the points we've touched on. So some of the advantages of Roto-Jet. So reliability. It's fully compliant with the most stringent standards in the industry, whether that's API 610, 682, it's referenced in HI, it's referenced and specified in Aramco standards. Bearing system life exceeds the 25,000 hours needed for API. Number one advantage is they are flexible. So very low vibration levels, can operate back on curve. If there's any uncertainty or upset in the process, this is a very good technology to promote. And again, that ability to run all the way from closed valve to 120% of BEP, you cannot do with a conventional pump, and you really cannot do with something like an OH6. So again, safe, there's no emissions to atmosphere, you don't have any pulsations to worry about either. Cost-effective point of view, again, there is no one size fits all, but there are certain points within that low flow, high head tombstone that these fit incredibly well. Sometimes there will be the lowest cost to start with. Sometimes there'll be the lowest cost operationally. Sometimes there'll be neither. Okay, and it's very important that we recognize that. And that statement is true for every type of pump we've mentioned in this presentation. What we do feel, however, is these kind of pumps pick up a disproportionately low percentage of the market. And it's our mission to make sure that we change that over the next few years, because there are far more applications that these are suited to that they're not selling into than the other way around. One of the questions we get a lot is around efficiency. Again, there's 1,000,001 points you can hit within any head and flow tombstone. There are certain spots where these will be the most efficient solution. As we mentioned right at the start, for these ultra low flows, where it's very common to have a Barsky type OH2 at 6, 7, 8, 9, 10% efficiency, these would go in on an equivalent duty and be able to achieve in excess of 40. So within certain areas, they are incredibly efficient. Within other areas, they are as efficient. And once you get past 440 US GPM, 100 meters cubed, it's about a wash with a conventional centrifugal pump. And in terms of uptime, that's the real winner here. And it's because of the flexibility and the robustness of the design. Okay. And with that, we'll say thank you very much for listening. And what we'll do is we have a few questions that's come in. And the first of which I will direct to Steve, which is, are these only manufactured within the USA?
Well, historically, they have only been in the USA, but under the footprint of Trillium, it's been expanded where we can offer our pitot tube pump technology manufactured in our facility in Nova Milanese in Trillium Pumps, Italy. So they're actually made in Europe and the United States today.
Perfect. Thank you, Steve. We had another one is, can these replace an OH6, which I hope we answered with a case study. And the answer is yes, they absolutely can. Obviously need to take into account pipe work constraints, footprint, etc. But as a short answer, yes, there is always a creative way that these can be made to replace an OH6, although it very often does require some work with the end user. Another one, Steve, I'll pass to yourself, is what's the suction pressure limit? Someone has asked that they have a 2600 PSI application, and would that be suitable for the Roto-Jet?
We'll have to take a closer look at the application, but the suction pressure limits are at 300 PSI. and 2600 looks on the surface to be maybe just outside of the capabilities, but if we have the full design conditions, we'll take a look and we can get back to you directly and discuss those.
Thank you, Steve. And the last question was on efficiency, which I hope we touched with the last comments. There really isn't one magical answer on that. The efficiencies at times will be beneficial, at times they'll be worse, and very often they'll also be a wash and unlikely comparable. It's important when we talk about efficiency that while it is an important factor, uptime, maintenance, full life cycle cost is really what we need to factor in. Energy consumption is always the biggest cost with pumps, so efficiency is always very, very important. But we do, as we showed with the case study and some of the repair bills, we do need to make sure we're looking at uptime as well, and full maintenance cost. So with that, I'll say thank you very much. I think that wraps us up for questions, and thank you everyone for your time and attention.